An answer for question 3 to the week 3 quiz. Here is the information we're provided. We're presented with two normally distributed graphs. We're told one of them is for the population and the other is for the sampling distribution of that population's sample mean. Axis titles have been deliberately omitted, but now that you've seen an answer to question 2, we can add those, and that would be the probability density being measured on this axis. And on this axis we're measuring both x values for the random variable that's representing the population, and also when it comes to the sampling distribution we're measuring on this axis the mean of x, another random variable. So the random variable is being measured, two random variables are actually being measured on this scale. The first question asks us to match the graphs above with either the probability distribution for the population or the sampling distribution of the sample mean. Now the first thing to do is to look at these two graphs and say, well, what's different about them and what's the same? They both have the same mean. Back from question 2 we saw that the mean of a normal distribution was the same as its mode, and that meant that it was at the maximum point, or the highest probability point in that particular distribution. So the mean for each is 2000. And what's different about them then is that B is a little bit more spread out than A. So it has a larger dispersion, and this would be consistent with B having larger standard deviation, which is equivalent to having larger variance. So just to answer the question then we have to say which will have the larger dispersion, would the sampling distribution of the mean or the population values have a larger dispersion? And the answer is that the sampling distribution has the smaller variance. So that would mean A has the smaller dispersion, it's more concentrated around its mean, so the sampling distribution will be A and the population distribution will be B. Now bear in mind that the sampling distribution is not looking at the distribution for a particular sample. It's looking at us taking repeated samples, lots of samples, calculating the sample mean for each one, and then looking at how those various sample means map out into a distribution. And because when you calculate the sample mean, you tend to average out or average away the extreme values from the population. So for example, here's our population. If in my sample I chose a value down here from the population plus another value that was, say, from here in the population, another one that was here, and let's say it was a really small sample like 3, those 3 values, 1, 2 and 3, which are quite far apart in terms of the population, when we calculate the mean of them, it's the average, and for these 3 we'd get an average somewhere fairly close to the mean. So this is why when we're looking at the distribution of sample means, because each sample mean is kind of averaging values from the population, the distribution of our sample means tends to be much more concentrated with a lower dispersion. And that's really the answer to part 2 here. You'd say A has lower dispersion. You could say standard deviation or variance, and something along the lines of which would be expected for the sampling distribution of the mean. The final question asks us, aside from the mean of the population, mu, so we can't use that in our answer, identify two other constants that would be influenced by the that would have influenced the shape of the sampling distribution considered above. So what are the main things that influence the shape of the sampling distribution? When it's normally distributed, there are two parameters. Those two parameters are the mean and the variance. Now this, what I've just shown here, is for the population. When it comes to the sampling distribution of the mean, these characteristics are, we can see, back up here in the graph, that the mean or expected value of both the probability distributions is the same. It's this 2000, so those two are identical. But the sampling distribution of the mean has as its variance the population variance, divided by n. So what this tells us is that we can have different sampling distributions of the mean. That's why this question up here says for a sampling distribution of the mean. We can have a sampling distribution of the sample mean with sample sizes of 3, and I gave you one example of that before, or we could have a sampling distribution where every sample that we took when we were calculating the mean was, say, 10. That would give us a different sampling distribution. Or we could take samples where everyone was, say, of size 100, and that would give us a different sampling distribution. In fact, what you'd see as I increase the sample size is that the sampling distribution would get more and more concentrated around this mean value, so with a lower and lower variance. And we can see that in this formula down here for the sampling distribution of the mean. It's saying that for a given sampling distribution, the variance is affected by n, and the larger this n gets, the smaller the overall value of the variance of the sampling distribution will be. So our answer is, to this question, the constants, well, that one's already been ruled out. Here's one thing, the variance for the population, and the second thing is sample size, n. So there's the answer.